This is Chemistry Chapter 12, Lecture 1. So in your chemistry textbook, we'll be starting on page 383 and get your Chapter 12 notes out and ready to go. I'll just quickly go through the bullet points on the Chapter 12 notes. You, of course, should be reading the chapter and following along that way. So pressure is force per unit area exerted on an object. Gas molecules are always colliding with objects, and those collisions exert a force, and the more collisions mean more pressure. You can think of air pressure as like the weight of the air. Okay, some of the pressure units are pascals, millimeters of mercury, torr. We'll use atmospheres a lot. We're going to use atmospheres, millimeters of mercury, and torr. Now, you may have heard of something called a barometer, so I want to explain that real quick. So with the barometer, you basically have a tube that is sitting inside a container that is filled with mercury, which is a very heavy liquid metal, and up at the top we have a vacuum. Okay, so there's no molecules, no air, nothing there. All right, and then the air exerts a pressure on the mercury in, we'll just call it the dish, okay, air pressure. The weight of the air. Now, on a normal day, the height, of course, that mercury then fills up this tube, fills up this column. And on a normal day, the height of that column is 760 millimeters. Okay, so on a high pressure day, the air would be heavier, and the mercury in the column would rise. There's nothing in the vacuum to resist it, so it would rise. And on a low pressure day, the weight of the air is lower, so the mercury in the column would fall. All right, so but on your average day, we would have a height of mercury in the column of 760 millimeters. So that's one way to measure air pressure. All right, moving on down your notes, the next thing that we talk about is Boyle's law. And Boyle's law relates pressure and volume. So you can just think of it as P1 V1 is equal to P2 V2. So this is your original condition. We could call that before. And let's say some things change, and this would be after. All right, so let's say volume changes, then pressure would adjust to change. And I've got a couple of videos linked in the description box to explain Boyle's law. All right, but you can read the definition. As long as temperature remains the same, the product of a gas's volume and pressure is always the same. So pressure times volume is going to equal some constant. All right, if pressure goes down, volume will go up. If volume goes down, pressure will go up. You can look in your book at the famous Boyle's law demonstration or on page 385. So it shows a container and how if we take the volume of the container and reduce it, then you're going to increase pressure because you would have more collisions. All right, so I've got links to some videos that talk about that. So that's Boyle's law. Charles's law talks about the relationship between volume and temperature. So we can think of that as the initial volume over the initial temperature has to equal the new volume over the new temperature. So again, this is some sort of before and after situation. So you can think of it as volume divided by temperature is equal to some constant. So in this case, if volume goes up, temperature would have to go up. Right? If volume goes down, temperature would have to go down, okay, in the same proportion. Okay, so volume divided by temperature is always constant. Now, we use this in Chapter 2. The Kelvin temperature scale is what we have to use with Charles's law because it's an absolute scale. So it's degrees Celsius plus 273.15. All right, so you need to memorize this, which you've probably already memorized it because we used it in prior chapters. All right, so the combined gas law is going to be the equation that we're going to utilize in this chapter. All right, so Boyle's law and Charles's law, if you combine the two, we have this equation. P1 V1 over T1 is equal to P2 V2 over T2. So again, this is a before and after situation. So we've had, let's say we have some changes in volume and temperature. We can figure out how the pressure changed. All right, so again, in the description box, you need to click on the videos that I've provided. These are videos that I would show in class. And they will help explain, illustrate these laws. All right, well, go ahead and flip the page in your notes and we will do the math with the combined gas law. All right, so we are at the top of page 2. Temperature must always be in Kelvin. Volume and pressure units have to be consistent. Okay, so if we are on pressure, if we're in torr, we have to stay in torr. If we are in milliliters, we have to stay in milliliters. Okay, so open your book, flip over to On Your Own 12.1. So we're on page 394. So this problem says a gas is stored in a metal cylinder with a volume that can't change. If the gas is packed into the cylinder at 0 degrees Celsius, a pressure of 3,415 kilopascals, what will the pressure inside the cylinder be when it's stored at a room temperature of 25 degrees C? All right, so we're going to, anytime you see a before and after situation, you use the combined gas law. Right? We don't want to get this confused with the ideal gas law that we'll learn later on in the chapter. Okay, so it says the volume can't change. If the volume can't change, we get to just mark it out because mathematically it will be the same on both sides, so it doesn't affect our calculations. All right, it says we want to know what will the pressure inside the cylinder be. All right, so the pressure, we're looking for P2. All right, so we've got P1 over T1, since I get to mark out the volume, is equal to P2 over T2. All right, we're trying to get P2. The way that you work this algebraically then is we take that T2 and bring it up here. So we'd have P2 is equal to P1 T2 over T1. I recommend circling the one you want and then drawing some arrows to help you figure out, solve it by letters, solve it by variables first. So now we're just going to plug in. P1 if you look at the problem, the initial pressure, so again, this is before and after, the initial pressure is 3,415 kilopascals. The second temperature, T2, is 25 degrees C, but we have to add that, all right? T2 is going to be 25 plus 273.15, so that's 298.15 Kelvin. And then the initial temperature is 0 Celsius. Well, that would be 273.15 Kelvin. We have to change this to Kelvin, right? If it was 0 Celsius, then we would be dividing by 0, right? That we'd get an error in our calculator. All right, so that is going to be 3,727.6, and the pressure units would stay in kilopascals. All right, let's do 12.2. Right underneath 12.1 says at room temperature, a normal atmospheric pressure is 1 atmosphere. All right, our pressure units were in kilopascals, now they're in atmospheres. The average person's lungs have a total capacity of 5.5 liters. If a person takes a deep breath and dives into a lake where the temperature is only 19 degrees C and the pressure is 915 torr, what will the new volume of the air be in his or her lungs? All right, so again, we have a before and after situation. P1 V1 over T1 is equal to P2 V2 over T2. All right, we are looking for the new volume. Okay, so we're looking for V2. So algebraically, we don't get to cancel anything out here. It doesn't say that volume or pressure can't change. So we bring T2 up here. That's the same as multiplying both sides by T2. And then dividing both sides by P2, that's the same as bringing P2 down here. So V2 is going to be P1 V1 T2 over T1 P2. Now we just have to be careful and plug in the right numbers from reading the problems. P1, our initial pressure, is 1 atmosphere. All right. But we're going to need to change that. I'll do that in a minute. Okay, we're going to need to change that to torr. Okay, so, but we'll fix that in just a second. Our initial volume of the lung is 5.5 liters. Our second temperature is 19 degrees Celsius. All right, that's going to be 19 plus 273.15. That would be 292.15. Again, I'm about to change this 1 atmosphere. So hopefully you wrote in pencil. And T1, our initial temperature, 25 degrees C. So that's going to be 298.15. Our second pressure is 915 torr. So down in the lake, pressure goes up. Now on the first page of your notes, we know that 1 atmosphere of pressure is equal to 760 torr. It's going to be easier then for you to change this problem from atmospheres to torr. You could also convert torrs to atmospheres. All right, if you did that, it'd be 915 divided by 760. All right, but 1 atmosphere is equal to 760 torr. Right? We have to have our pressure in the same units. All right, so be careful putting this in your calculator. I'd probably do the numerator, multiply those 3 together, get an answer, and then divide it by the denominator. All right, so it'd be 760 times 5.5 times 292.15, then hit equals, you'll have an answer, and then hit divided by, left parenthesis, 298.15 times 915. Okay, So make sure that you put the bottom, so you'll have that top answer from your calculator, and then hit divide by, and then 298.15 times 915, and then right parentheses. If you'll do that, then you won't accidentally get the wrong answer due to order of operations. But the volume in the lungs is going to go down. You increase the pressure, it's going to go down to 4.48 liters. So make sure you try that and try to get that in your calculator correct. Again, 760 times 5.5 times 292.15, all right, and hit equal. That'll give you an answer. Hit divide by 298.15 times 915. Put that in parentheses. All right, let me see if I can fill out 12.3 down here at the bottom. So 12.3, we have, if you fill a balloon with air to a volume of 2.31 liters at a room temperature of 25 degrees C, what volume will the balloon have if you put it in the freezer? Assume the pressure stays constant. Well, it would make sense if you put it in the freezer that the volume would go down. You can try that at home if you want. But so we have V1. Let me do that again. P1 V1 over T1 is equal to P2 V2 over T2, before and after. The pressure remains constant. Okay, so that makes sense because a freezer is inside your house. It's going to have the same pressure pretty much as your house. V2 is what we're trying to get. What is the new volume? So we're going to bring T2 up there. So V2 is equal to V1 T2 over T1. Right? So V2, our original volume of the balloon is 2.31 liters. Our second temperature is minus 5 degrees Celsius. So minus 5, so in this case, I'll just put it up here, minus 5 plus 273.15 would give you 268.15. And then we're going to divide that by the original temperature, 25 degrees C. That's 298.15. All right, if you put that in the calculator, again, you can do 2.31 times 268.15, hit equal and get an answer, and then divide that by 298.15. You would get 2.08 liters. So you don't want to make a calculator error on these. You get it set up all right, do the algebra, get all the numbers right, and then your calculator, you have a calculator error. Now let's flip the page. We're just going to look at the very top of page 3. So this will help you answer some of the review questions that are coming up. Pause the video if you need to as I erase. All right, we're going to talk about ideal gases. All right, gases behave ideally when the molecules that make up the gas are very small compared to the total volume. That's usually the case. Molecules that make up the gas are far enough apart they have no attraction or repulsion. Usually the case. If it's a gas, the molecules are usually far apart. Otherwise, they'd be a liquid or a solid. No energy is lost during collisions, so we call it collisions are elastic. That's more of a physics concept if you ever take physics. Gases behave ideally. You're going to need to memorize this. High temperature. In chemistry, high temperature is 273 Kelvin and above. All right, so 273 plus. All right, high temperature, low pressure in chemistry is 1 atmosphere and below. So 273 Kelvin and above That's high temperature, even though that's 0 Celsius, so it's actually cold to human beings. And 1 atmosphere and below. Standard temperature and pressure. Okay, you've got to memorize this because a lot of problems use the term STP. What is standard temperature and pressure? Well, the temperature is going to be 273 K. Standard pressure is 1 atmosphere. All right, that would also be 760 torr or 760 millimeters of mercury. Okay, but that's standard temperature and pressure. If you want to do 273.15, that's totally fine. I really don't care either way. So the homework that goes with this lecture would be review questions, page 415, 1 through 7. Practice problems, page 416, 1 through 3. All right, that does it for Chapter 12, Lecture 1, and I will talk to you next video.